Today we are going to take a look at enthalpies of formation and another method of finding the change in enthalpy for a reaction. We have looked at adding multi-step reactions together to find the overall change in enthalpy, and now we're going to take a look at a second method using what are called enthalpies of formation and introducing what those are. Why do we need another method for finding delta H? So we found it using the specific heat equation, Q equals mc delta T, because Q is actually equal to our change in enthalpy for a chemical reaction. We've also used the multi-step reactions and added them to find our change in enthalpy, or delta H. And now we will look at a third calculation. This is based off of what we call enthalpies of formation. And the reason we have these different methods is because we often have limited resources in finding information. So we're only given specific information and we have to use what we are given to find our answers. So in enthalpy of formation, we have a reaction presented here. Carbon, which is a solid, plus oxygen gas, O2, is giving us carbon dioxide gas. And the change in enthalpy for this reaction is negative 393.5 kilojoules per mole. The reaction shows the formation of exactly 1 mole of carbon dioxide gas from each of its elements in what we call the standard state. The standard state for an element is its elemental form. So carbon comes all by itself, just one carbon atom at a time. That's the simplest form of it. Oxygen always comes as O2. It's one of our 7 diatomic elements. So it comes as O2. And together those perfectly form carbon dioxide, CO2, 1 mole of it. The amount of energy that it takes to form that single mole of carbon dioxide is at negative 393.5 kilojoules. So it's actually exothermic. It gives off that energy. And the units for that are kilojoules per mole. So for every mole of carbon dioxide made, we give off that amount of energy. If we were to multiply all the coefficients on this reaction by something like 2, then we would give off twice the amount of energy. So the change in enthalpy value for this reaction is called the enthalpy of formation for carbon dioxide. We commonly see it written as delta H with the little F at the bottom for formation and a little circle. It looks like a degrees sign, but it's not a not symbol, and it means standard state. So when we see that F and we see that little knot, we can know that that value was measured for that chemical from its elemental forms. The size of an enthalpy change for a substance depends on the temperature, pressure, and state, so solid, liquid, or gas, of the reactants and products. So standard conditions are needed for these measurements. Under standard conditions, the change in enthalpy of formation has been measured. So all of these values that we will be using for enthalpies of formation have been measured under these conditions. So the standard state of a substance is when it's in its pure form, it's at 1 atmosphere of pressure, and usually the temperature of 25 degrees Celsius. And they pick 25 degrees Celsius because it is room temperature. We can also look at it as 298 Kelvin. So all of these measurements will have been made at under those conditions, and that's where that little knot symbol comes from. It's under standard conditions, and it's in that elemental form. So the enthalpy of formation of a compound, delta H, not F, is the change in enthalpy for the reaction that forms 1 mole of the compound from its elements with all substances in their standard states. So if the chemicals come as elements in their standard state and form a compound, 1 mole of that compound in its standard state, then our change in enthalpy will equal our change in enthalpy of formation. For example, we have in this reaction 2 carbon atoms in their graphite form, so just like in your pencil, plus hydrogen gas, H2, because it's diatomic, forming C2H2, and it's forming 1 mole of that product. So since the reactants are in their standard states and it's forming 1 mole of product, our change in enthalpy value, 226.7 kilojoules per mole, is also called the enthalpy of formation of C2H2. The enthalpy of formation, a key thing to remember here, is the enthalpy of formation for the carbon and hydrogen atoms themselves, or molecules, is 0, because it doesn't need to form. It already exists in nature. So substances in their elemental form do not have a standard enthalpy of formation, or their standard enthalpy of formation is 0. We will be looking up our delta H, or change in enthalpy of formation, values in our textbook. We have Appendix C in your textbook beginning on page 1059. Make sure you write that down in your notes and put a big box and a star by it, because you will need to find those values. They are listed in alphabetical order by the first element in the compound. So if you're trying to look up something that starts in carbon, you're going to look under C, so it'll go things that start with A and then B and then C. So we'll see elements like argon first, then things like boron and barium, and then our carbons and coppers and things like that. So it will go in alphabetical order. Using enthalpies of formation to calculate enthalpies of reaction. We can apply Hess's law in a completely new way using enthalpies of formation. So we can write formation equations for each of the compounds in this reaction at the top. So we have C3H8 plus 5 oxygen molecules forming 3 carbon dioxide molecules and 4 water molecules. So looking at this reaction, we have a couple of pieces that are really critical. We have the C3H8, which we call propane. You'd be familiar with that name. So the first reaction below says 3 carbon as a solid plus 4 water molecules forming C3H8, or propane. So the enthalpy of formation of that propane is negative 103.85 kilojoules per mole. The second thing that's key here is our carbon dioxide. So to make the carbon dioxide, we have solid carbon, 1 mole of it, plus 1 mole of oxygen, making our 1 mole of carbon dioxide. And our last component is our water. So hydrogen molecule plus half an oxygen molecule gives us our 1 mole of water. So we do have that half oxygen. That's a little odd for you guys. So you can split the oxygen and think of it as 1 atom of oxygen, because we really, when we're writing these enthalpies of formation, we only want to make 1 mole. So to do that, we would have to have half the oxygen molecule. And we have our enthalpy of formation of water, which is negative 241.8 kilojoules per mole. Now, the oxygen up at the top in the reaction, this combustion, does not have a reaction below because oxygen's enthalpy of formation is 0. It doesn't take energy to form oxygen because it's already found like that in nature. So what we've done before is take these three reactions, or reactions like them, and manipulate them around to form the reaction up at the top. So for instance, this first reaction has our propane, but it's on the wrong side. So we would flip this reaction and change it to a positive value for delta H. Our second reaction, we need 3 carbon dioxide, so we would multiply this reaction by 3 and leave it how it is otherwise, and multiply our delta H by 3. And then for the water, we would multiply the water by 4, and then we would multiply our delta H by 4. And then after that, we would use that idea to help add up these reactions and find our delta H for the reaction at the top. We can then change the reactions to get the proper coefficients and get the chemicals into the correct place. Our first reaction, we decided to flip, so we get the propane on the correct side, so that flips the sign from negative to positive for our delta H. Our second reaction, we multiply by a coefficient of 3, so the delta H also multiplies by 3. And the third reaction, we multiply by a coefficient of 4, and so our delta H multiplies by a coefficient of 4. We can now see that the carbon in the first reaction and the hydrogen in the first reaction will cross out with carbon and hydrogen in the other two reactions, and that our oxygen in reactions 2 and 3 will add up to the 5 oxygen needed in the original reaction up at the top, our goal. So even though we didn't have a separate reaction for oxygen, it still is included and it still ends up in our final reaction. So now we have all of our reactions written out with their proper coefficients, and we are going to multiply each of the reactions, or each of the enthalpies, by their proper number to get our number of moles to cancel out. So for our first reaction, since we did not multiply it by a coefficient or by another number, we're really multiplying it by 1. We did flip its sign, but we're using 1 mole of the propane, C3H8. So we're going to multiply its delta H of formation by 1 mole. Since we used 3 times the amount of carbon dioxide, we multiply its delta H by 3 moles. And since we use 4 times the amount of water, we're going to multiply its delta H by 4. We can see that each of these, when we multiply by their moles, the moles will cancel out, and we are simply left with kilojoules, the units for change in enthalpy. Now, if we look at this process to do all of this, once we multiply out these enthalpies of formation by their coefficients and then add up all those numbers, we've gone through a really lengthy process to get to a delta H value, because we would have to write all of those reactions out for each chemical and then manipulate the chemicals and the reactions and add up all these values. So there is a way to simplify all of this, which is very nice for us. So this is kind of the process we've seen before, and now we're going to simplify it. We can calculate the change in enthalpy for the reaction. It ends up being negative 2043.9 kilojoules. Every time this is done, we end up taking the change in enthalpy of formation values for the products multiplying them by their coefficients or numbers of moles, then flipping the sign for the reactants and multiplying them by their coefficients. Anything in standard state is left out because it has no enthalpy of formation. So we can take this idea and actually put that pattern together into an equation. So our equation we can write for delta H of the reaction from the enthalpies of formations looks like this. It's a little bit crazy looking when you first look at it, but it's not hard to use. So it says the change in enthalpy of a reaction at standard state, with a little not sign, equals sigma, which is the sum of N, which means the number of moles, times the change in enthalpy of formation of the products, minus the sum of the number of moles of the change in enthalpy of formation of the reactants. So we're going to take our enthalpies of our products and subtract our enthalpies of our reactants. That negative there takes care of flipping the sign for our reactants. We saw in our previous, when we were doing the long example, the propane, C3H8, ended up needing to, the reaction had to be flipped. Well, that would occur every time if we were to do it the long way. So instead of having to flip the sign, we subtract, and it takes care of that. So using that same example, this is what our equation would end up looking like. We have, let's kind of break this down. So we have N, which is number of moles. So it's 3 moles of carbon dioxide, it's our first product, times the enthalpy of formation of that product for carbon dioxide. We're going to add to that because it's the sum of our water. So we have 4 moles of water times its enthalpy of formation for the water. So all of that is for our products. Then we subtract, so there's our subtraction, our reactants. We have 1 mole of propane times its enthalpy of formation. I want you to go ahead and try this in your calculator and just check your work and make sure you understand how to calculate this out. But you should get negative 2,043.9 kilojoules for your answer. When we deal with sig figs, just as a reminder, we are adding and subtracting here, so we want to round to the lowest number of decimal places. We can see that our enthalpies, 2 of them have 1 decimal place and the other one has 2 decimal places, so we're going to round to 1 single decimal place. So for our second example, we're going to take a look at the reaction of what's called methanol or methyl alcohol. So it says what is the standard enthalpy of reaction using the values below. So we have methanol plus oxygen, we're combusting it, forming carbon dioxide and water. So in our table, which you would find a similar one in your book, listing all of the chemicals with their standard enthalpies of formation, we've got our methanol, our carbon dioxide, and our water. It is really key to pay attention to the states of matter. For instance, water will be listed as a liquid or a gas, so you want to make sure you're using the correct value. So to find this, our change in enthalpy of our reaction, we are going to use our reaction, or use our equation that we saw on the previous slides. So the sum of the number of moles of enthalpy values for the products. So our first product is carbon dioxide. We have 2 moles of carbon dioxide times its value from the table, so negative 393.5 kilojoules per mole. You can see the moles will end up canceling out. We're going to add that to our other product. Our other product is water, and we have 4 moles of it. So 4 moles times the value for the water. And that gives us our products. And then we're going to subtract the reactants. We have 2 moles of our methanol times its value, negative 239 kilojoules, 239 kilojoules per mole. We do not have to include the oxygen because the oxygen is in its standard state, and it doesn't have an enthalpy of formation. Its enthalpy of formation is 0, so it will not affect our calculation. So we have our 2 times our enthalpy of formation, we get negative 787 kilojoules. The 4 times the negative 286, we get negative 1,144 kilojoules. And then 2 times the negative 39, we get negative 487 kilojoules. So we do our calculation here, and we end up with negative 1,444 kilojoules of energy. So to burn methanol, 2 moles of methanol, we will give off 1,444 kilojoules of energy. So you can see it's a pretty straightforward method of calculating this. We just have to get used to the equation. Now I will warn you, when we get our equation sheet for our test, for the AP test, it does not include the N, the number of moles here, which is a mystery to me, but it's something we have to remember. We do need to multiply by the moles, though, to give us just those kilojoules for our delta H values. What I want you guys to do now is take some time and practice these 3 questions. Use the chart, the enthalpies of formation, in your book, and the equation to calculate the change in enthalpy for each reaction. You have 3 reactions here, and I want you to be careful with those states that matter when you're looking up the values. I do want you to show your work on these in your notes, try them out, and that will make sure that you're actually doing this, and I want to see those when I check your notes. So pause the video, try these out, and then on the next slide we will get the answers. You'll really pause the video. Alright, so here are the answers for your calculations. For the first one we have negative 1,366.7 kilojoules. For the second, we have negative 129.73 kilojoules. And for the third one, we have positive 2,538.9 kilojoules. So the first 2 are exothermic reactions, so getting off energy. Our third one is taking in energy. It is labeled as photosynthesis. Photosynthesis is our process that stores energy in chemical bonds of glucose for plants. It's endothermic, so plants take in the energy from the sun, and they store that energy in the glucose molecules that are formed. And then we are able to use that energy by eating what the plants are making, like eating our vegetables. And now for your joke. Exothermic reactions. I studied them before they were cool. Haha. Have a great day, guys.